Over the next several classes, we're going to be talking about thermodynamics, and in this set of videos, I want to give us the foundational theories and concepts that are really the bedrock of thermodynamics, the terminology and the concepts upon which the first and second laws are based. To begin, let's talk about the nature of energy. Energy is an absolutely central concept in thermodynamics. Before diving in there, I do want to talk a little bit about our motivations for studying thermodynamics. So the figure that you see here on the slide shows us directly how thermodynamics can benefit our everyday lives. It shows the primary energy consumption per real dollar of GDP from about 1950 to about 2010. Something that may surprise you is that the curve is sloping downward. Although it seems like we're using more energy every day, the energy consumption per dollar of GDP has actually decreased over time. Part of the reason for this is that we've learned how to harness energy more efficiently. Energy is a scarce commodity. We want to understand how it works so that we can harness it efficiently. There's also more to energy than meets the eye. We'll talk about spontaneous processes and irreversible processes and what's called the arrow of time, the idea that certain processes cannot be reversed and only go in the forward direction. From the perspective of a chemist, chemical reactions always involve some transfer of energy. So we want to know, when will such energy transfers be dangerous, and when will a reaction go at all? Chemical thermodynamics really gives us deep insights into these questions, as well as how bulk properties, like pressure for example, arise from molecular level effects. One last reason for studying thermodynamics is that it's just fascinating. One good example that I like to give is entropy of mixing, the idea that two pure substances will spontaneously mix when in contact, not by virtue really of anything to do with energy, but because entropy drives mixing. We'll talk about that in a later video. All right, but before getting there, let's talk about what is energy. I want you to think about now your general notion of an energetic person or object. What are the characteristics of that person, for example? Well, here's one example of a fairly famous energetic person. Jim Cramer is the host of the show Mad Money on CNN, and he's well known for his sort of crazy, frenetic style. He's mobile, he's active, he's unpredictable. This is a good example of an energetic person. So we think of energetic people as mobile, hot, unpredictable. The formal definition in thermodynamics is energy is the capacity for a system to do work or transfer heat. These two ways to transfer energy, work and heat, are related on a deep level, which we'll talk about later. We are going to make an important distinction between external and internal energy, and in fact, we won't really be concerned with external energy. So I do want to talk about that distinction here briefly. So what do we mean by external energy? Well, as we'll talk about very soon, thermodynamics makes a distinction between the system and the surroundings. And any motion of the system as a whole, for example, imagine our system is just a box sitting on Earth. Motion of the box as the Earth moves around the sun, for an example, is an example of external kinetic energy. The motion of the entire system is irrelevant to what's going on within the system internally. External potential energy has to do with any external potentials, like the gravitational potential, that are acting uniformly on a system. So for example, if a system is experiencing a downward pull due to gravity, but the entire system is experiencing a uniform pull, well then this is external potential energy, and it's irrelevant to the behavior of the system itself within the system. What we're more interested in for the purposes of thermodynamics is internal energy. Well, internal energy includes only the kinetic energy and potential energies of particles within the system. So if we imagine our system, for example, as a bunch of ideal gas particles, the internal kinetic energy of the system is just the kinetic energy of those particles as they buzz around inside the box. And the internal potential energy is just, for example, the intermolecular forces, the intermolecular interactions between those particles. That invokes nothing from the surroundings, nothing from the outside. We'll denote internal energy using the symbol U. Let's talk now about the units of energy that we'll typically see. The SI unit of energy is known as the joule, and it's equal to 1 Newton meter. It takes 1 joule of energy to move 1 Newton of force through a distance of 1 meter. And this is roughly the work required to lift an apple about a meter off of the ground. So if we were to take an apple off of a table, for example, and lift it to a height of 1 meter, that corresponds to 1 joule of energy, or 1 joule of work. You'll see chemists often use the unit, the calorie, which is the energy required to raise the temperature of 1 gram of water by 1 degree C, and this is equal to about 4.187 joules. So the joule and the calorie are both fairly small units, especially when we start talking about moles worth of chemical materials. So you'll often see kilojoules, kilocalories, even in some contexts, mega and gigajoules, mega and gigacalories. At other scales, smaller units are more appropriate. So the electron volt, for example, is a common unit at the molecular or microscopic scale. This is the energy required to move an electron whose charge is just the elementary charge, negative E, through a potential difference of 1 volt. That's equal to about 1.6 times 10 to the negative 19 joules. Extremely tiny, right, to move a single electron through a potential difference of 1 volt. Another small unit of energy is the erg, which is 1/10 of 1 microjoule, or 1 times 10 to the negative 7 joules. But the joule and the calorie are the two most common units of energy that you'll see.